Hi everyone, welcome back to the channel. This video is going to be on dimensional analysis and it'll be helpful for your AP Chemistry or um, normal Chem 1 course. So first off, I have a few practice problems, but I'm going to start off with just some basics of dimensional analysis and um, why it works kind of. So we all know that there's different types of units, right? So for example, 1 inch is equal to 2.54 centimeters. So if you divide both sides by, let's say 1 inch, right? And this cancels out and you just get 1 here. The unit goes away because you're dividing this by 1 inch. So all this cancels out. This just equals 1. This is called a conversion factor. You can use this and multiply it to any value. And because it's equal to 1, it's not going to alter the number in any way. So for example, if you need to convert 10 centimeters into 1 inch, instead of having to think about, well, do I divide by 2.54 centimeters or multiply by 2.54 centimeters, you can just write it out. And that may seem easy because obviously you're dividing because you want a smaller number in inches, but when the calculations get really long, it's helpful to just have one calculation rather than relying on thinking about each step individually. So you would just do 10 centimeters times and times, and then this conversion factor, we want to rearrange it so that the centimeters will cancel out. Like this unit should cancel out basically, so that we're left with inches. So we can do that by taking the inverse of this. So we can write 1 inch on the top, and then 2.54 centimeters on the bottom. And now notice the centimeters unit cancels out, right? And we're left with 10 times 1 inch over 2.54 centimeters. And then you get a number in inches. So that's how you convert. And this can like go through multiple steps if you're dealing with more complicated conversions or conversion factors. So we'll take a look at our first problem now. So our first problem is convert a rate of 96.0 cubic feet per minute into cubic centimeters per second. So we have a rate of 96.0 feet cubed per minute. And we want to convert this unit into centimeters cubed per second. So notice that our numerator unit is changing and our denominator is changing as well. And also it's important to note that we have a cubic unit here, cubic feet and cubic centimeters. And that's going to play a role in our dimensional analysis calculations. It'll be slightly different than this simple like linear unit here. So we can start out by writing what we're given, which is 96 cubic feet per minute. And now we have to multiply this by a certain conversion factor that helps us get closer to this final unit over here. So for now, let's deal with the denominator first, because it's pretty simple. To get from minutes to seconds, we have 1 minute on the top because we want this unit to cancel out here. And then 1 minute is equal to 60 seconds. So we can write that in the denominator. So now we've successfully change the denominator to seconds, and if we were to end the calculation right here, our final answer would be in cubic feet per second, but we want cubic centimeters, so we're going to have to change this unit over here. So we know that 1 foot is equal to 12 inches, right? So if we were to do this, we get an incorrect answer because the units aren't canceling out correctly. In fact, this would become squared feet because we're dividing by just like 1 foot over here. So we have to cube this conversion factor so that we get the correct units to cancel out. So when we cube the conversion factor or square it, raising it to any exponent, we can't just put 3 over here. This isn't equivalent. 1 foot is equal to 12 centimeters, but 1 foot cubed is not equal to 12 inches cubed. This is not equivalent. The reason why is because when we do this, we're ignoring the numerical value here. For example, if I were to draw a cube, right? And all of these sides were 1 foot, all of these sides. If we find the volume of this, we would get 1 foot cubed. But 1 foot is equal to 12 inches, right? We know that here, just the linear version. It's equal to 12 inches, right? So now I have to substitute each one of these dimensions by substitute each one of these with inches, not inches cubed. So that means I would get 12 inches on this side, 12 inches on this side, and then 12 on this side. And notice when we take the volume of this, it's going to be 12 cubed inches cubed. And this is the correct, this is equal to 1 foot cubed, not this. This is incorrect. We need the cube over there because the numerical value itself is also being cubed. So in order to change this, we can put a parentheses. I like doing this because you can see that the normal conversion factor inside the parentheses is equal, and then you're just cubing the entire number, which is like, remember over here, each conversion factor is equal to 1. So we're essentially just like cubing this 1, if that makes sense, by doing this, which are equivalent. So now we've converted the feet cubed into inches cubed. So we're a little closer now because now we know that 1 inch is equal to 2.54 centimeters. So we can do one more conversion factor over here, and this time it'd be 1 inch cubed, and then 2.54 centimeters cubed. Okay, so now we've got the seconds in the denominator. Feet cubed cancels out to inches cubed, and then that cancels out as well, and we're left with centimeters cubed over seconds. So we have the correct unit now. So all we need to do is just complete this numerical conversion, and we'll get our answer. So the answer here, if you put into your calculator, is going to be 45,300 centimeters cubed per second. So take a look here. In our question, we're given 96.0 cubic feet. So since we're in a chemistry class, we're going to have to pay attention to the significant figures. So the number of sig figs in our given value is 3. So that means our final answer should match that, and we should have 3. So we only have 3 over here. These zeros aren't part of the significant figures. So this is our final answer for this problem. Okay, so our next problem is, a statue is plated with silver foil. The surface area of the foil that is exposed to outside air is 2,150 centimeters squared. If 8.344 grams of silver were used to plate the statue, and the density of the silver foil is 10.49 grams per centimeter cubed, what is the thickness of the foil in millimeters? Okay, so this is slightly more complicated. So we're given a statue. So I'm just going to draw it like this. And by the way, if a problem ever seems kind of convoluted or complicated, drawing a diagram just like might help, and like playing out what you're trying to, like what the goal is, if that makes sense. Because you have to start with a value and end at a certain value. So it's helpful to sort of think about the steps that you would take to get to that final answer. So we're given that the surface area of this statue, the silver foil. So we have a statue here, but silver foil is only plated on the outside of it. So the surface area of that foil is this number right here. So we have 2,150 centimeters cubed, and it says that if 8.344 grams of silver were used, and we're given the density as well. So we can take a look and connect the pieces here. So density is going to be mass over volume, right? We have the mass of silver that's given to us right here, this value over here. So we have the mass in this conversion factor, and then it says over volume, but we're only given the area basically. So we're missing another dimension, and that's where this thickness comes in. So essentially what this problem is saying is that if we were to multiply this surface area of the foil by the thickness, it would give us a volume, right? Because we have 3 dimensions now. And we can use that volume and then to um, use this conversion factor. So in this case, it's a little flipped because typically you would assume that they give you the volume and then you have to calculate the mass, or they give you the mass and you have to calculate the volume. But now they give you the mass, but you don't have to calculate the volume because two of the dimensions in the volume are already given here. So you just need the thickness. So we can solve for the volume, but just divide it by this value over here, and that would give us the thickness of the foil. Because it gives you this area, right, which is the surface area, but you're missing this, which is the thickness, and that's what they want as the answer. So we can just solve for that. So we can start out with 8.344 grams of silver, and then this density here is also conversion factor because it's saying that 10.49 grams of silver is also equal to 1 centimeter cubed of silver. So that's a conversion factor as well. That's equal to 1 essentially. So we can put this in the denominator, and then 1 centimeter cubed. So now we've converted this mass into a volume, and now we want the thickness, right? So we're going to want to divide this volume by the surface area that's given. So this isn't very typical, but just so that we have all of our work in one line, I'm going to write it like this. But you could separate this into two different equations. One calculating for the volume, like stopping right here. But you can also add this here because you're going to eventually divide it by 2,150 centimeters squared. So when we do this, the grams cancel out. But notice here, this fully cancels out, but this 3 just becomes a 1. So we're left with centimeters, which is like the linear term, right? And that's going to give us our answer because we want the thickness. So we're dividing the volume by the area, which is going to give us the thickness of the silver. So once you compute this, oh, I missed one more step. It wants the answer in millimeters. So instead of stopping here, we can just do another conversion factors. So right now we have our thickness in centimeters, but we need to convert that centimeters into millimeters. So you can do this two ways. You can go from centimeters to meters and then meters to millimeters, or you can just do centimeters to millimeters, which is 10 millimeters per centimeter. So I'm going to do it into meters because might not. So 100 centimeters is equal to 1 meter times, and then 1 meter is equal to 10 to the power of 3 millimeters. Sorry, so this is done here. And now if you compute this equation and put it into your calculator, you get a final answer of 0.00370 millimeters. So notice how we have 3 sig figs over here. These both have 4, but our answer in chemistry is limited by the least accurate estimation here. So our least accurate estimation is this one because it has the least amount of significant figures. So our final answer should have 3 significant figures. So this is our final answer. Okay, so for our last problem, a building server room measures 15.0 feet by 20.0 feet by 8.00 feet. The room contains soundproof acoustic panels made of a polyurethane polymer. During an accidental fire, the panels may release carbon monoxide gas. If the panels release exactly 0.54 grams of carbon monoxide for every square foot of panel burned, what is the maximum surface area of the paneling in square yards that can burn before the concentration of CO throughout the entire room reaches 1.20 times 10 to the power of negative 3 grams per liter? Okay, so that was a lot of information. So essentially what this question is asking is, we have a room with a certain volume given, and we have given the measurements of this room, which is up here. So we have to calculate how much of CO2 can be released to get this ratio kind of. So this grams per liter ratio. So it's saying that we have a certain amount of CO2 that's burnt off that enters this room over here, and it's asking us like how much CO2 can be burnt, how much CO2 needs to burn to reach this ratio. But it adds one more layer to that. Instead of asking for the mass, right, which we're given, it's saying that it's adding one more ratio here. For every square foot of panel burned, this many grams of CO are released. So we have to use that, and our final answer is going to be in square yards because that's what it wants. Because it's asking what the maximum surface area of paneling can be burned. So this is gonna link to this over here. That's going to be towards the end of our calculation. So I feel like the problem with this is that many people don't know where to start here because we're given 3 different values, but only it makes it easier to start with one of these 3. So notice how one value is given up here, and then this value, this 0.54 grams for every square foot, is basically a conversion factor here. Grams of CO per square foot. So if you were to start with this, we wouldn't really have anywhere to go because our final answer is in square yards, right? But that requires only one more step after this. But we're ignoring the fact that all of this other information is given. So it doesn't make sense to start with this because this is going to be a conversion factor that we're going to use later in our calculation. This is going to be like one of the last things we need to use because it directly leads us to the surface area of the paneling, right? Which is what we want. And then we're also given one more conversion factor, which is this one over here, 1.20 times 10 to the power negative 3. And notice how this has a unit of liters in the denominator. So that could be helpful because we're given feet cubed up here, right? That's the volume. So if we start, for example, to map this out, if we started with the volume of the room, we would use this conversion factor, and that would give us the mass of CO that can be released to produce this specific ratio that they want. And then we can go take another step further using this one, this conversion factor, because we're given the mass and we're also given the square foot of paneling, right? So we can use this to determine how much paneling can be burnt. And then all of this is basically to answer the question of when it reaches this, when the ratio of CO in the room to volume is this ratio essentially. So it's going to be helpful to start with this value right here. Sorry, it's going to be helpful to start with this value over here. So first, our volume, right? That's going to be the first step. So we can just multiply all of the dimensions given, and we get a volume of 2,400 feet cubed. And now we need to convert this into liters, right? Because that's going to allow us to use, for the second step, to use this conversion factor over here. So I feel like the easiest way you can do this is first by converting the feet cubed into inches cubed, and then going to centimeters cubed, and then milliliters, and then liters. So we can start this off by converting into inches. This is going to be 12 inches. And then remember, we're going to cube both of these. And then we have to convert the inches into centimeters. So 1 inch cubed is going to be 2.54 centimeters cubed. And then we know this is a common number or conversion factor you should know for your class. 1 centimeter cubed is equal to 1 milliliter cubed by definition. So these are like equal to each other always. So now you can say 1 centimeter cubed is equal to 1 milliliter. So notice here how before we were using these this cubed, we were cubing these values, right? But notice how here we're not cubing milliliters. This is because you can think of this as a linear conversion, because 1 cubic centimeter is equal to 1 milliliter. You don't need to cube this because it's already a unit of volume, right? So there's no reason to cube this because you have this conversion factor by definition. It's true always. So now we can continue going, and 1000 milliliters is equal to 1 liter. So notice how, once again, I'm making sure that all these conversion factors line up so that these units cancel out perfectly with each other. So now I've got to the volume, right? So we just need to do one more step to get to the mass of CO, which is going to be to use this 1.20 times 10 to the power of negative 3 ratio. So I'm going to put liters on the bottom and then mass on the top. Okay, so now we've finally got to the mass of CO. So if you were to stop here, it's good to think like this. So if you were to stop here, we would get the mass of CO2 released that would produce this ratio. So now let's take a pause here and see what else we have to do. So if we were to stop here, we get the mass, right? But the question is asking us for the maximum surface area of paneling. So that's where we would use this last conversion factor over here to get to the final answer, which is the area of paneling. So 0.54 grams of CO are released with every square foot of paneling burnt. So we can put that over here. And then cubic or squared foot would go on top. Now we cancel this out. So if we were to stop here, we would get the paneling burnt in feet squared. But our question is asking us in square yards. So we just need to take one more step here. And then we'll get our answer. So 1 foot or 3 feet is equal to 1 yard. But now we have to square this because we're dealing with feet squared and yard squared. And so now if we were to take stop here and do all this numerical calculation, we would get a final answer of 20.1 yards squared. So once again, for the sig figs, we're going to have 3 sig figs in our answer, because if you take a look here, so we have 3 measurements, each are that with 3 sig figs, and then this ratio has 3 sig figs. But if you look here, this number over here has, if you at first glance, it has 2 sig figs, right? The 4 and the 5. But notice how it says each panel's release exactly 0.45. So that means that this number is you can think of it as a 0.45000 in infinite zeros after this, because it's exactly 0.45. So this is not gonna limit our sig figs. So in that case, we're gonna look at the other 2 numbers, and we have 3 sig figs here and 3 over here. So our final answer should have 3 sig figs, which is 20.1 yards squared. So yeah, that's it on the dimensional analysis video. And once again, this is going to be useful for AP chemistry and honors chemistry, or CP chemistry as well. I hope this video helps you guys. Thanks for watching.